As discussed from the previous lesson, this is our second lesson. It's all about calculation of the total impedance when you're doing the combination of the three components. What should be the total value of those combination, and it's called to be an impedance. So you're going to have a look today on a Rlc circuit, which is basically the combination of a resistor and a capacitor, your Rl circuit, resistor and inductor, and then your Rlc, the combination of the three. And we're gonna do some example on each, and I want you to master how to calculate this total impedance, the combination of these three components. When it comes to Rlc circuit, as we said, it's all about a combination of a resistor and an inductor. Okay, so we have discussed already our pure inductor, pure resistor. When we combine the two, they are not anymore pure. But when we come, for instance, we want to do our calculation, and then we are only focused on the inductor, it's become pure. But when you look at the two together like this, they are not pure anymore. This become an impedance. Okay, so how do we calculate it? It's all about, as we said, with a pure resistance, is always at an angle of 0. Pure capacitor, it's always at minus 90. Okay, because when we are dealing with a 0 degree, 90, 180, so you should be used to it, 270, until you back to 0, or you can say 0 minus 90 minus 180, and then you have your minus 270 until you back to 0. Okay, that's just what we are doing there. So with a pure resistance at 0, pure capacitor at minus 90, because remember we are doing the combination of the two, so we have to add the two vector. Okay, when you add the two vector, you're gonna have this impedance. This vector, it's gonna be the impedance. The impedance is just a combination of the two components. So you wanna choose any triangle. Okay, once you choose any triangle, you apply your Pythagoras. Once you apply your Pythagoras, this is gonna be the Pythagoras formula, and then we often use this formula just to calculate a unknown component. For instance, if our resistor is unknown, we can calculate it using this Pythagoras. But in order for us to calculate the total impedance, we need to have it in complex form. As we say, electrical 2 is all about complex form, and therefore the total impedance of a combination of a resistor and a capacitor, it's gonna be R minus J XC, which I'm going to show you how to do it with your calculator over the phone. It's just a quick video for the register student. Okay, so as we said, a note that we have to keep in mind is that when it comes to a capacitor, we're going to expect the current that will be leading the voltage. So we're going to have a power factor that will be leading. Okay, so the concept of the power factor will be explained in the next video. So let's have a look on some example and see how we can do a calculation. So take your time to understand it, and I think the video law, once it uploads, there will be a free day, 1 or 2 days, for you to ask question if you have some challenge doing calculation for this total impedance. So they give us a resistor in ohm value, they give us a capacitor in ohm value, which we call to be a capacitance, and as we say from our formula, the total impedance, the combination of the two, will be given by this complex formula, and therefore this is your rectangular form, or you can change it to to polar form. Okay, or another way to calculate it, remember you are in the series. In series, the two components add each other, so it's going to be R plus X. So basically when you're doing it in this form, it's like you're doing pure component. So you know, with a pure resistance is always at the angle of 0. A pure capacitor is always at minus 90, and therefore your final answer will be the same. Then someone will apply this formula, but with this The thing is, you need to make sure that you know that if a pure resistance always at 0, pure capacitor is at minus 90, and then you add them like that to get your final answer. And in the second example, you have a value of the resistance in ohm, but the capacitor is given in farad. So we need to change it to a ohm value. We need to change this to a ohm value. So you apply this formula of the capacitance, then you change it to RMS value, because here they give us the frequency, and then from here you can calculate your total impedance as we did with the first example. Well, let's have a look on the Rl circuit. As we said, it's all about a combination of a resistor and an inductor. Okay, so we know that with a pure inductor, is that resistor is always at the angle of 0, pure inductor always at the angle of 90 degrees. The addition of the two vectors will give us an impedance. This vector will be the impedance angle. So if you come here, this triangle, you apply your Pythagoras, you are going to have this as the Pythagoras formula. But remember, it's all about complex calculation. This will be your total impedance when you're calculating the total impedance. The first one will help you just to calculate an unknown component. Okay, so therefore once you apply this formula, okay, one thing we know with an inductor, if the current is flowing, the inductor is a battery of storage of current, so there will be a delay to the current. Any delay to the current, it's going to be called lagging. It's going to give us a lagging power factor. The concept of the power factor will be discussed in the next video, which means the current is lagging the voltage, it's coming behind the voltage. So we're gonna have some example on it as well. When you come here, one thing we observe is that they give us a resistor, they give us an inductance because it's ohm value. So you come here from the formula, you know that our impedance is going to be given by this equation, and this is in rectangular form and that is in polar form, which I will explain how to do it, or someone else can do the calculation as pure component. So if pure component, just take the value of this resistor but give it a pure angle which is 0, and then you take the value of your inductance, give it a pure angle of 90, because a pure inductor is always at the angle of 90, and therefore you're gonna have the same answer as for the first one. And then in this case, they give us a resistor and they give us an inductor, which we know we need to change it to a ohm value, and therefore we can do our calculation as we did with the previous example. And then the last one, which gonna be the RLC circuit. When it comes to the RLC circuit, because remember, the two circuits may affect, we either gonna have a leading or lagging. So we're gonna have two cases. The first case, we're gonna have when the capacitance is greater than the inductance. The second case, XL is greater than XC. So we're just gonna compare their ohm value, which one is bigger than which one. So how do we do that? Let's take the case where our inductance is greater than XC. Okay, so let's have a look. Pure resistance at the angle of 0, pure inductance at the angle of 90, pure capacitor at the angle of minus 90. As you can see from their vector, this vector is smaller than XL. Okay, so you do the projection of XC here. So it's going to give you this small vector, which is going to be our XL minus XC vector. So if you apply the vector method to calculate the total impedance, we are going to have that this as our total impedance. Then you pick one of the triangle, you apply your Pythagoras. If you apply your Pythagoras, you're gonna have this as the equation, okay, because of that vector, Okay, so it's gonna be r squared plus, okay, so you use this one to calculate a unknown component, and now you use this one to calculate the total impedance, because everything should be in complex mode. And then we say when our XL, which is an inductor, is greater, which means we're going to have a power factor which is going to be lagging. The concept of the power factor will be explained in the next video. Okay, so that's how you do it. Okay, so lagging, it means the current is coming behind the voltage. And when it comes to a XC which is greater than XL, we're going to explain it as well. We have a pure resistance at the angle of 0, a pure capacitor always at the angle of -90, a pure inductor at the angle of 90. When you project that vector, you're going to have this vector which is going to be XC minus XL, because the bigger one is the capacitance. And then when you apply your vector method to calculate the total impedance, what you have, you're going to have this vector which is total impedance, and then you choose one triangle, you apply your Pythagore. Once you apply your Pythagore, what you see is that you're going to have this equation which we say it helps you to calculate an unknown component, but when it comes to the value of the real total impedance is this one, because it's in rectangular form, it's in complex mode. Okay, and therefore our power factor is going to be leading, because XC is the most dominant one, and then when the circuit is capacitive, we're going to have a leading power factor, which means the current is coming before the voltage, and this concept will be discussed in the next video. Let's have our last example. First of all, they give us a resistor, they give us an inductance, and they give us a capacitor. And as we say, we need to compare the two, and if you compare, we can see that this one is greater than the capacitance. So I need to apply the formula in the case where our XL is greater than XC. So it's going to be XL minus XC. Okay, and therefore you have your answer. Okay, and the theme is applied here. It's going to be positive minus XL minus XC. Okay, and then this is in polar form, that is in rectangular form, or you can deal with them as pure component. When it comes to pure component, because they're in series, they must add each other. Okay, but make sure you take the value of the resistance, but you give it a pure angle which is 0. The value of the inductance, you give it a pure angle which is 90. A pure capacitor, then you give it an angle of minus 90. Therefore you're gonna get the same answer as the one who did it in that form. Okay, but in the second example, what happened now is that they give you them in Henry, and then you give them in Farad. So the first thing you need to change is to change them to ohm value. You change this to ohm value, and then you compare the two. You can see that XC is greater than XL. Okay, so if XC is greater than XL, what's happened now? You're gonna come here, you do calculation. Okay, so you're gonna apply this formula, because XC is greater than XL, and therefore you're gonna get your total impedance, or you can treat them as a pure component, and therefore you apply this, you give them their pure angle, and then that's how you do it. In the next video, as I said, we're going to discuss about the power factor, which is really an important part in order for us to move forward. After this, tomorrow, the third lesson video, now we can start doing calculation of the series circuit. But already with what we did today, you already have a lesson on series circuit. But what is missing is that part of power factor and power calculation.